Welcome to today's industry expert panel discussion on the topic of getting started in water circularity, how to really achieve 90% water savings, presented by the Resource Innovation Institute. The USDA has estimated that 80% of water consumption in the US is from agriculture, with rates as high as 90% in some Western states. Of course, water is used for more than irrigation in controlled environment agriculture, or CEA. Greenhouses in arid regions may use as much water cooling the air with evaporative pad systems as they do irrigating the plants. Hydroponic facilities purifying their source water with reverse osmosis membrane technology are typically creating 1 gallon of brine waste for every 1 to 2 gallons of purified water that they use. And it's not just the volume of wastewater being produced, but what's inside it. Irrigation runoff contains nitrogen and phosphorus that can lead to algae blooms in natural waterways, and pest control chemicals can harm aquatic life. My name is Rob Eddy. I'm the Resource Efficiency Horticulturalist for RII. Joining me today as the technology wizard behind the curtain is Brennan McMillan from RII. Today's webinar is being recorded. It's being recorded, and all registrants will receive a copy of the recording and the slide deck, because we have a lot of great information for you today, and which we don't want you to miss. There's advice for everyone here, whether you're taking a first look at reducing your wastewater or you're considering investing in or upgrading your water treatment equipment for full recirculation. We'd like to thank our sponsor, the USDA Natural Resources Conservation Service. We also want to acknowledge the cleanwater3.org, a USDA specialty crops research initiative that helps growers reduce, remediate, and recycle irrigation water. Brennan will post their website, Clean Water 3, which includes an amazing amount of water circularity information and online tools. So check that out when you get a moment. So here's the agenda for our hour together. I'm going to introduce our panel. I'm going to do a short slide presentation. Then we're going to have about a 20-minute discussion with me and our panelists. Then at the end, we're going to open it up to questions and answers from the audience. At any point in the presentation today, you can ask questions using the question and answer button on your Zoom screen. And we'll get to those as many as those as possible in the Q&A. All right. So anytime you want to ask a question, just jot it down there. All right, we'll move on. Our subject matter experts, Our subject matter experts joining me today bring global experience in precision irrigation, nutrient management, water treatment, and water circularity design. I'll start the introductions off, then I'll let Kyle and then Andy introduce themselves, their companies, and answer this one easy question: what brings you and your company to focus on water circularity? So I'll go first. Rob Eddy, as I said, my background is in greenhouse management. I was at Purdue University for 20 years as their plant growth facilities manager. That's the biggest chunk of my career. What brings me to focus on water circularity is that as a young grower, I wasted a lot of water and fertilizer. And working for RII and taking up this subject in particular gives me a chance to kind of offset some of that waste by teaching others not to do that. Kyle, go ahead, introduce yourselves and tell us a little bit about your company.
Hey, Rob, thank you. Thank you for inviting me back. Thank you, RII, and looking forward to this discussion. So I focus my career on water resources with an emphasis on water reuse opportunities, mainly within the private sector. The majority of my experience has been in large agricultural applications. And I've really grown a passion for it throughout my career, and enjoy the challenges of identifying new and innovative ways to use water efficiently. Arco Murray is a leader in design, construction, and commissioning of commercial greenhouses and indoor farms here in the U.S. Arco Murray is a design-build firm that builds a lot of different buildings for different industries, but we're here to talk about the CEA space. After working alongside Arco Murray for a number of years, I joined the company to assist in launching Blue Water, which is a subsidiary company providing water treatment and water management solutions to our clients. Our current projects include water treatment water reuse, monitoring, and compliance programs for our CEA clients, as well as other ag and industrial sectors. And for the purpose of this call, I want to add that our experience spans a wide variety of crop production methods integrated into greenhouse and indoor and vertical farming facilities. So thanks again, Rob.
You bet. Andy, tell us a little bit about yourself and your company.
Yeah, hi, Andy from, I'm here in Amsterdam at the moment. I have a crop technical background in hydroponic greenhouse vegetable production now for a little over 25 years. I'm now responsible for Grodan's knowledge program. So a little bit about Grodan. Grodan manufacture steerable stonewall growing media solutions, so both substrates and sensors, and then we support that through structured user advice. So we're active globally, and we're active in greenhouse, high-tech greenhouse vegetable crops, cannabis, and also strawberries right now. So we have quite a broad knowledge program that extends across those three crop groups, and I've got a finger in all three pies. So to give you an example, now we're investigating nutrient water uptake in low heat input systems for greenhouses. Obviously, energy management is a big issue. We're also investigating irrigation management strategies for high-tech strawberries and cannabis.
Great. Thank you, Andy. Thank you, Kyle. So great to have the two of you here. And I know you're both on, well, I know Kyle's on a job site and Andy's in the airport in Amsterdam. So appreciate your extra effort to join us today. A little bit about RII, who we are. We're a nonprofit public-private partnership advancing climate resilience. We provide resource efficiency education, training, and verification services in collaboration with CEA producers, researchers, governments, utilities, and the design and construction sector. We benchmark growers' productivity and resource efficiency for energy, water, emissions using our Power Score platform. We establish working groups to develop best practices guides and provide education, vocational training in several forms. Here's a couple of those publications. On the left is the Water Circularity Best Practices Guide, just released this summer. And just a short time after that, the CEA Energy and Water Benchmarking Report was released, which is some of the first data from CEA operations in the US with validated utility level energy and water use. All the slides you're going to see today are from those publications. Much like today's webinar, these guides blend industry-informed content with academic research and engineering advancements, providing non-biased information that we believe is unique. It's our mission to create resources for the industries, ones you'll use repeatedly. So here's a chart from that benchmarking report about water. The oft-repeated claim of 90% water savings of CEA operations compared to field production is not a myth and can be achieved. It's not easy, but it can be achieved. This sample graph from our benchmarking report of leafy greens producers shows a broad range of water usage measured in gallons used per pound of harvested product. Two of the producers on the far left were capable of growing using only 3 gallons or less per pound, which is in fact a 90% savings over cited research on field production. Of course, irrigation water is not the only source of waste in a CEA facility. So let's talk about what some of the others are, why we're here. Here's a chart from the Best Practices Guide. The 8 rows represent waste sources that we've priority ranked. Each column in the table is an aspect of that waste that we use to determine the ranking for priority. Some of these wastes, I won't go through this whole thing. You can look it up yourself in the guide, and we'll put that in the chat, a link to that catalog that has this guide in it. But I'll explain a little bit. That leachate is terminology for the water that comes out the bottom of the pot or the bottom of the stone wall slab. RO reject is reverse osmosis wastewater that I discussed earlier. Evaporative cooling bleed off is the water that's put, always bled off the reservoir or of a cooling pad inside a greenhouse to keep it from getting too high in salts. And condensate is what collects on coils of HVAC and dehumidification units as it cools the air or dehumidifies the air. So there's a lot of water waste streams to consider, but here's why irrigation is the highest ranking. One, it's relevant to all facilities, so it's something we all can get into and start with. It has a potential for high volume, that's for sure. The release of it causes environmental harm. Again, we've talked about that with the nitrogen and phosphorus. And lastly, the potential to improve the ROI on the treatment costs is high with this kind of wastewater. And why is that? Reducing irrigation waste saves significant water, of course, to be sure, but those water savings alone don't justify the cost of recirculating water. It's not cheap. But because CA facilities irrigate with fertilizer solutions, the cost of that fertilizer can be cut by 40 to 50%. Fertilizer costs have been spiking in recent years. You can see from this graph of the last 7 years of fertilizer prices. So basically, any fertilizer water going down the drain is money going down the drain. So what can we do about it? Well, here's some of the proven technologies for reducing irrigation waste. You're probably all familiar with drip irrigation to conserve water. Also used are precision water booms, ebb and flood tables, and in fully scaled facilities, flood floors. You can kind of see that in the image on the right. The legacy floriculture and vegetable industries have proven these technologies over the last several decades. Irrigation can also be triggered more efficiently using weight scales combined with smart irrigation programming. So this reduces waste because you're not overwatering. These scales are prevalent in greenhouse production of tomatoes, roses, and sometimes strawberries. Andy will talk about this throughout today's discussion. On the right, you can see that the apparatus includes not just weight scales, but sensors that measure the volume of water and electrical conductivity of the water that drains out of those slabs. So that allows for fine tuning not only of the irrigation by measuring the volume, but of the fertilizer by measuring the EC, which is electrical conductivity. Here's a graph of research I did at Purdue University with a poinsettia crop over 3 months using soil moisture sensors, or otherwise known as water content sensing. During the first 2 months of manual watering, you can see the water content. The line of the graph is all over the place. This is a peat-based substrate typically used in greenhouses. But the last month, in the little blue box, using soil moisture sensors is very uniform. Comes on at the same time, always saturates, and then you can see several days for it to dry out. Peat and coco coir based root substrates hold water and nutrients for the plants to use over 1 day or more days than that. And this way you could say these are more forgiving root substrates and little errors don't result in a lot of crop losses that are visible. On the other hand, overwatering and fertilizer imbalances happen pretty frequently without the grower even being aware. It's kind of like, some of these soils, peat and coir, they're kind of like a black box. But what's the alternative? Those drawbacks, those aspects of irrigation are not true when you're getting into the commercial scale of, say, hydroponic tomatoes grown in stone wool, as pictured here. You can see a little water sensor up there in the upper right too. Stone wool dries out very quickly and basically doesn't accumulate nutrients for later use. So the plant roots rely on the frequent and precise irrigation, sometimes up to 20 times per day. First time I heard this, I was just astounded. I thought that's crazy. This kind of precision requires automation to achieve, but the year-round yields and quality tomatoes that growers can achieve, it's just simply astounding. I'm not the one to talk about this. I'm going to show you a graph next, and I'd like Andy to chime in a little bit about interpreting this graph of water content and EC. Andy, do you mind jumping in here for a little bit and explaining this?
Yeah, for sure, Rob. Thanks. what you see here is a schematic representation of what the sensor would display in real time when it's in the slab. So we've got the green line is the representing the water content. So peaks and troughs are representing irrigation, and the blue dotted line is representing the EC in the substrate. Yeah, so not in the drain, in the substrate. And essentially, we split this diagram or this graphic into three phases. So phase one, we talk about resaturating the slab. Yeah, so we've got this stepwise increase in water content. And generally in that phase, we tend to use large irrigation volumes. Why? Well, to get back to the same day level water content, we've got to account for the decrease in phase three plus what the plant's evaporating during phase one. Now, as we move into phase two, you see the water content line plateau and the EC line decline. So this is kind of the drain period. And what's really important to notice here is for EC control in the substrate, the irrigations around that first drain, you can see have the biggest effect on leveling or lowering the EC in the stone wall. So if you were setting up your irrigation strategy here in phase two, you would like to see, for example, EC lowest when the radiation is highest. So these lines that can also be sent to the climate computer, and you can add more data points to them. Yeah. So what we would add to this graphic is the light sum and the light intensity. Yeah. So in phase two, we like to see is EC lowest when radiation is highest. And then at some point we would like to stop irrigation, and you can see that irrigation is stopped sometime before sunset. So in our user advice or the settings of the climate computer, this stop time can be optimized. Likewise, as you move forwards now into phase one of day two, so the far end of on the right hand side of this graphic, you will see basically the sensor, the water content line change. Yeah, the slope will change as the plant begins to transpire. And this is then, of course, the optimum time to start irrigation. So between stopping in phase two of day one and starting in phase one of day two, yeah, we get a constant decrease in water content overnight. Yeah, and the stop times and the start times can vary based on the outside weather conditions. Yeah, this not only provides stability for the plant in its growth and development, but also protects root quality, and that's fundamentally important. And during the growing cycle of the crop, we can vary the absolute value of the water content. Yeah, we can vary the absolute value of the EC. So for example, in winter, when the weather is dark, we would steer with a low day level water content and a high EC. And we may want a larger decrease in water content overnight than, for example, in the summer. So typically in winter, we might be looking for 10-15% decrease in water content. In summer, it might be 8 to 10%. So essentially, we can use this graphic and experience to translate into a structured irrigation strategy on the climate computer or whatever tool is controlling your irrigation.
Great. Thank you, Andy. And I love hearing those details, particularly from someone who does this every day. In the best practices guide, we also talk about the details of smart programming based on having irrigation based on threshold of sunlight on accumulated sunlight called DLI, or even more sophisticated that based on weather prediction forecasts and other such variables. So dig into that best practices guide for more information at that detail level. Of course, irrigation water can also be reduced by eliminating the horticultural substrate altogether and using hydroponics, recirculating hydroponics, right? Many different forms are available. I'm not going to go into them here. Of course, they're in a best practices guide. The CE industry has pioneered unique designs, including vertical hydroponics. The benefits and considerations of each are detailed in that guide. Of course, water treatment is a big part of the guide as well. At least 25% is taken up by discussion of the physical, chemical, and biological treatment technologies that are out there. We believe the charts that we have put into the guide, as you see here, we're not going to dig into them, but we believe they're the most updated, detailed charts of the attributes of nearly every kind of water treatment, be it physical, chemical, or biological. The charts compare what types of contaminants each technology controls, the reaction time required for that control, the residual effect, if any, of that control, the relative size of the equipment, so you know how when you're designing a water technology room, how much space you'll need, and the relative costs of the equipment. Your approach with water treatment for recirculation will always be layered. It'll never be just one thing. You'll need at least some kind of filtration, then something instant that does instantaneous disinfection or purification, and then something that has a residual control effect for downstream in the pipes, right? A quick example is you might have a cartridge filter, and then UV light for disinfection, and then ozone for disinfection that lasts downstream into the pipes, into all the drippers or the ebb and flood tables, whatever you're using. The reason you need that residual control will be to control biofilm. Okay, biofilm is bad.
Hey,
news.
Rob.
Yeah,
Rob,
please.
can I just mention one thing on your last
Yeah,
slide,
please. Yeah.
I want to emphasize that there was so much collaboration over such an extensive period of time to develop these tables. This was not one or two select vendors who came up with these, but RII really took it upon themselves to reach out and collaborate with academia, growers, water treatment vendors to come up with this list. It's quite robust. To Rob's point, it is quite extensive and up to date and compared to some of the other tables out there. So I just wanted to hit on the vast number of resources that it took to come up with these tables.
Oh, that's so kind of you. Thank you. And it was fun. We had tables like this that we modified, and we gave credit to the folks who we use. I believe it was a Canadian Research Institute that we used as a model. But then, like you said, then we talked to academics and we talked to our working group and updated it. Thank you for that. Biofilm, this is stuff that is fairly new to me. I'm used to, as a greenhouse manager, having drippers get clogged and things getting slimy, any sort of water, anything containing water in it. But I didn't really know how insidious biofilms are. It's waterborne bacteria that attaches to the surface of pipes, hoses, reservoirs, anything with water and organic matter or nutrients. These are going to form. They exude substances. They attach and they exude substances that allow it to form a matrix that protects them from the typical disinfection technologies. Then they grow, and then they disperse more waterborne bacteria, a bit like a mushroom releases spores into the air, right? Imagine that in your pipes. They not only clog the lines and drippers, but they harbor plant diseases, root diseases, and even foodborne diseases that make people sick. So this has to be one of your top priorities when you're recirculating water, having something that will help control this. Here are a few of here are the control options. These 5 are the ones that we know control biofilm. So this will probably be one of these will probably be in your system. Because of this, it's a priority water treatment and controlled only by this handful. Okay. Here we go. We're going to move on to a new topic now. Let's talk about alternative water sources. One of the most potent strategies in water circularity is to use an alternative water source to supplement or even replace the use of groundwater, surface water, municipal water, whatever your source is. Though not possible everywhere, of course, rainwater and HVAC-D or HVAC dehumidification condensate, those are 2 examples of what you can use, nearly pure sources. We'll start with HVAC-D condensate, and I really want Kyle to comment on this because he has experience with how this works. But I want to tell you, a 2020 study showed that 2/3 of the annual water demand of a lettuce vertical farm could be supplied from this condensate supply. This is water that originally been used as irrigation water. Then it transpired through the plant and then condensed on the coils of the HVAC unit or the dehumidification units. So it's completing that irrigation loop in full circle. Kyle, you've dealt with this a lot. Can you talk about some of the challenges of HVAC condensate, recapture and treatment?
Sure. Yeah, I mean, controlled environment ag presents a unique opportunity to reuse a large volume of water in condensate capture and reclaim. Condensate's not specific to controlled environment farms. We have condensate in any controlled building like this hotel I'm in, but we're generating a lot of condensate because we're controlling the humidity and capturing that evapotranspiration, and the result is a pretty substantial amount of water volume. Now, that water can be easily collected, treated, and reused if you have the proper infrastructure in place. And one of my biggest pieces of advice on this topic is try not to have it be an afterthought when you're building out your farm. And so what I mean by the proper infrastructure is the condensate is going to be generated from a number of mechanical systems in your farm, and we need to collect that water very efficiently and get it back to a single storage reservoir. And we need to treat it or condition it before we reuse it. Problems lie in stagnant areas of condensate, either low pitch piping on the collection system, or multiple areas where that condensate can lay stagnant and grow contaminants that we don't want. Why is that condensate growing contaminants? It is hyper pure water. It's distilled water that's been condensed, back into water. And it is picking up things from its environment, like VOCs in the air, or like heavy metals that it touches, or microbial spores. And so it is clean, but it can become dirty if, again, we don't collect it very efficiently, store it, and condition it prior to reuse. Another thing I'd add is it can be reused in a lot of different applications. So we talk often in this industry about reusing condensate to supplement irrigation water. Yes, and it is a great, if it's properly cleaned, it's a great input for hydroponic plant production water if it's conditioned prior to. But if you look inside controlled environment facilities, whether it's an indoor farm or a closed-style greenhouse, I would challenge you to take a look at your other, water needs from an operational perspective or mechanical perspective, and see what other non-potable or non-domestic water needs there are, and see if supplementing condensate for those needs makes more sense. Again, that kind of goes into a deeper topic on how to design your facility and what your overall water management strategy is. But the takeaway from this is it is a large volume of water in controlled facilities. Focus on collecting it efficiently, treating it, and reusing it where it makes the most sense.
Great, thanks, Kyle. And when you have these near pure water sources on hand, it means if your other source of water that you're using required RO technology to clean it up, you're not having to use that, or not having to use it as much. And as we said two times at least, that RO creates a lot of waste. So some regions of the U.S. receive enough rainfall to fully supply the irrigation needs of a CEA facility. One example, Metrolina greenhouses in North Carolina, they do not draw from the water table. They're completely self-sufficient. And so they're not subject to any regulations on that water. So they've kind of insured themselves from having to comply with regulations that might be expensive because they've already solved the problem. Of course, use of rainwater is routinely done in the Netherlands, where growers are required to have a storage capacity of at least 500 cubic meters of rainwater per hectare. That's about 53,000 gallons per acre in our terminology. And this can provide about 65% of their irrigation needs. Lastly, a quick word about storage. We talk about this in depth in the guide. Water can be stored either inside or outside, but obviously your geographic location will determine that. Understand if you're doing inside, or well, either way, it's going to take a lot of room. So a great deal of planning is required. You're going to need large doors to get the equipment in, or maybe bring in new equipment or take old equipment out. You definitely want access space around all sides of the equipment of at least 3 feet, so you can go after leaks and repairs and just make it ergonomic for your technicians to work there. Lastly, water should never be left stagnant in tanks, even if it's cleaned up. You need to have it circulated constantly through a disinfection loop, such as a UV light. So we've done the slide deck now. We're going to get into, I'm going to start with a couple of questions for our discussion with Kyle and Andy. Then we're going to go to some of the audience questions. A reminder, anytime you can type questions into the question and answer section of Zoom. Okay. Hope you're having as good a time as I am. I'm going to unshare this, so I'll bring that back later when I have to show one more figure that I'm going to have Kyle talk about. Andy, do you mind if I start with you? As a grower moves towards recirculating irrigation water, what water quality issues do they need to monitor more closely than before?
Well, Rob, I think there are 3 water quality issues. We call it the primary water supply: sodium, iron, and bicarbonate. Yeah. So if you've got a high iron content, yeah, you might want simple aeration to get rid of it. If you've got high bicarbonate content, you might want kind of a pre-acidification unit. But that said, the real killer is sodium. Yeah, so the plants do not take up sodium, and sodium is a positive ion. It's also an antagonist to things like calcium and potassium. So any sodium in your primary water supply will build up in a recirculating system. So ideally, you would use rainwater because it contains nothing. If you've got sodium in your system, then to get rid of that would be most likely require an RO machine. I think in the past, growers in the Netherlands were able to discharge drain water if the sodium levels reached 8 or 9 millimolar. Yeah, that was historic a long time ago. Now they can't discharge it at all. Yeah, it has to be completely closed. So sodium is the killer
because of regulations, right? Regulations in the Netherlands.
The regulations on drain water emission, basically you cannot emit anything back into the environment that isn't of the same quality that you got into your greenhouse. Yeah.
Thank you.
And that's driven by European legislation on the surface water quality to deal with the issues that you mentioned about nitrogen and phosphate in surface water, but also plant protection products. So you imagine a company like the Netherlands with 5,000 hectares all crammed into a very small area of intensive high-tech hydroponic greenhouses, and they have lots of standing water. So the legislation here is really driving drove that investment into completely closed systems. And as Grodan, we were involved in those trials back in 2014. So we first with the Wageningen University, and I think you've had speakers on Jin van Rijven for example. So we demonstrated that being 100% closed was possible. Yeah, 10 years ago actually. And those trials were focused with cucumber because it was fast growing, it was a quick win, and then pepper, yeah, because it was the hardest one to do. Yeah, so sodium is the killer.
Yeah, wonderful. Thank you for that. And a funny quick story is I worked for an operation that was tempering their water because it was so cold. They didn't want to water the plants with it, and they were tempering it in a boiler. And so they softened the water before they put it in the boiler to keep the boiler from scaling up. But they're softening it with, of course, sodium chloride. So they didn't realize they're adding so much sodium to their water. The mechanics didn't understand the implications.
Yeah, chloride is not an enemy. You know, you can use potassium chloride, but sodium is your enemy. Yeah.
Yeah. Kyle, I've heard you say that assessing your water source in the first place is how to get started in water circularity. How does that kind of assessment work, and how does it affect your planning and sizing of equipment and such? What's that like?
Yeah. Great stuff from Andy, by the way. I think it's going to segue into some of the other things we might talk about later in terms of membrane selection. But it also it is pertinent to, identifying your source waters and making sure your water quality is in line with your expectations. In prep for this call, I kind of narrowed it down to 4 simple questions that growers, owners, farm operators might want to remember and ask themselves. What are the characteristics of your source water? What are the characteristics of the water quality needed for operations? What is the water quality characteristics for plant production? And then if you're reusing or reclaiming water, what are the water quality characteristics of that water? You guys gave great examples. Why does it matter what type of operational water quality characteristics we need? Well, Rob, you just said, hey, we needed to soften the water for mechanical systems, for chillers, boilers, but we accidentally softened the water and had high sodium or chlorides that were also being used for plant production. So in that instance, whoever you contract to evaluate your incoming water qualities and design a treatment system around it, they need to talk to somebody like Andy. They need to talk to somebody like Andy and say, hey, what type of water quality do you need at the drip emitter? And they need to talk to somebody at the who's designing the mechanical equipment, the boilers, the chillers, the wet wall pads, the foggers. What type of water quality is needed here? And I'll go beyond just water quality, but also to those 2 applications, both operationally and in plant production. Water quality is a major aspect of it. But hydrologic conditions are also a factor in it. They need water at a certain temperature, at a certain flow rate, at a certain pressure. And all that is kind of combined in saying, okay, we've evaluated our source water quality. We know what's in there. We've consulted with the team that's going to design a treatment system to get our water quality to where we need it. And we're going to deliver it at the quality and quantity that's needed on the back end. And the last thing I'd add to that is I would get very, I would reach out and stay connected, if you're here in the United States, at least, to a state certified lab and understand what kind of services they can provide. Understand what you need to look at in terms of water quality constituents. If it's a city supply, then typically, the municipality will have water quality reports available to the public. But you're going to want to take some additional analysis through a lab that you establish a relationship with. And finally, what you're looking for. You're looking for not only inorganic constituents, dissolved constituents like the sodiums, the chlorides, dissolved ions, but you're also looking for organic compounds, PFAS compounds, different man-made constituents, And you want to make sure you have a good understanding of the overall makeup of that water quality, so that again you can size your treatment equipment and deliver the water to where you need to.
Great points. And I just learned last year that one of our university scientists had shown that the chlorine level in normal tap water was enough to cause damage in lettuce. So it's just one of those things, like you said, you need to ask an expert what kind of water you need coming out of that emitter, because there's something you would just assume that drinking water would be fine, but it may not be, depending on what you're growing.
I
Kyle,
would reiterate that, but basically, what you should do at the start of each cultivation is have your primary water supply analyzed. Yeah. Now, normally you can do it once, but if it changes, yeah. So, for example, you might be using your rainwater, yeah, and then you change to your bore. You need to get it analyzed again. So so you know what you're dealing with. That's the first thing. And secondly, to go for any nasty surprises in hydroponics, as the general rule is you do not use pond water, as in or river, yeah, because you don't know what's in there, yeah. So agricultural runoff, chemicals from the farming industry. So that is generally a no-go zone, yeah. So rainwater, bore water, and extreme cases because of the scale, yeah, it would be town water because it's more expensive, yeah.
Yeah, I'm glad you said that. I was surprised to learn that river water was most likely to have heavy metal contaminants in it, but then I continued reading. It was because this is in the United States, because we had so many factories dumping waste into our rivers. Luckily, we're beginning to clean that up. We've done a pretty good job in the last few decades, but it's a real issue with river water. So I'm glad you brought that up. Kyle, I do want to talk about membrane filtration, because I keep talking about we need something more efficient than RO, or we need to encourage growers to buy the most efficient RO units. But you know quite a bit about ultrafiltration, some of the other membrane technologies. Can I put an image up on the screen and have you talk a little bit about that?
Yeah, it's a great topic for this webinar, and we've just organically hit on a lot of the aspects of treatment selection and membrane selection that you want to look at. I don't want to make this too technical. I keep it very high level, but have the audience have some takeaway points. What I hear in the industry a lot, and we talk about a lot, is different membrane technologies and how they can be applied. Here in the United States, it's quite common for some of the indoor farms to use reverse osmosis to strip everything out of the water and then make a very precise and balanced recipe for hydroponic plant production. Traditional greenhouses here in the United States don't go as far as historically don't go as far as RO filtration, but it's really up to a grower and operator's preference. But the question I get a lot is, what's the difference between RO and ultrafiltration? Oh, RO is going to strip everything out of the water, most things out of the water, and give you a recovery rate between 50% recovery all the way upwards of 85, maybe even 90% recovery, depending on how it's sized and the pre-treatment and conditioning before it. So it's going to have a lower recovery rate and purer water. And then when you step up to ultrafiltration, ultrafiltration is basically just a larger pore size. Okay, so it's going to give you a higher recovery rate, but it's also going to allow some constituents through. And the constituents of concern in this instance are sodium, chloride, and hardness ions. And that's been the challenge, adopting ultrafiltration either as a pre-treatment stage for fresh water or as a recirculation technology for recirculating hydroponic plant production, because historically it's not removing the sodium ions that that Andy talked about earlier. That being said, there are some technologies out there that are advancing membrane technology, ion specific or ion selective membrane technology, and there's even some companies that are making them commercially available. You go down that route, I implore you to check them out. It's exciting stuff in terms of the water technology space. But ask questions. How long has this technology been around? What's the recovery rate? What's the replacement of the membrane or the maintenance costs? Hopefully a technology like that could be a good fit, for your operations. But the point on this is I wanted to make a distinction between RO membrane technology and ultrafiltration.
Fantastic. Thank you. Yeah, I want to get to some of the audience questions. We've gotten some good ones from the registrants as they signed up. And if you have typed in questions to our Q&A, please keep those coming. Andy's answered one of them. So we'll jump into these. Andy, I know we may have touched on this before, but one of the questions is what's the biggest risk to crops when recirculating water?
The biggest risk? Well, basically, apart from the buildup of sodium, of course, maintaining the correct balance of the individual nutrient ratios. Yeah. So basically, you need to be monitoring at least every 14 days, ideally every 7 days, the drain solution. So get the drain water solution analyzed, and then make sure that the adjustments that you make into the fertilizer stock tanks are informed. Yeah, and in that way you maintain correct ratios between the different nutrient elements.
Great point. And those go ahead.
Yeah, so sorry, the question I answered in the thing, we use a process called uptake analysis. So for example, we know the volume of irrigation that we've given, and we know the concentration of each individual element. We can also record the volume of drain that we get, and via the analysis, the concentration of each individual element. And essentially the difference is the uptake by the plant. And we know what the plant needs, and then we can adjust the feed recipe accordingly.
So you can kind of model the nutrient uptake. Let me see if I can restate that. You model the nutrient uptake of a crop by applying fertilizer in your systems that the analysis of, because you're constantly monitoring that. You're also constantly monitoring every 7 to 10 days the analysis of the drain water, so what the difference must be, what the plant is taking up. It can't go anywhere else. I think this must be called balance.
Yep. So it's called uptake analysis. So for example, a classic one is, growers might say, there's no nitrate in my drain water. Yeah, well, that's fine because it's all in the plant.
Yeah.
So the uptake analysis is a really useful tool. We use it in our trials, particularly with vegetables. And what's key, and why I say ideally you do this you monitor this every week, is because you don't want to make big changes. Yeah, so you want to keep the changes small. If you leave it 2 weeks, 3 weeks, 4 weeks, then you end up making a big change. Yeah, and that really is not good for stability in the growth of the plant. Yeah. So small changes by constant adjustment.
Thank you. Kyle, I'm going to ask you this one from one of our registrants. Can water circularity be done on a small scale in a cost-effective way?
Yeah, I absolutely think so. Again, evaluating in selecting the appropriate plant production system, and the right feedstock inputs. So when I say feedstock, the right nutrients, the right, water conditioning, whatnot. I think you'll get into a lot of challenges and issues if using a lot of organic based fertilizers or molasses, stuff like that on recirculating systems. It's going to cause a lot more maintenance and costs and labor. So keeping it very simple, if you have a small hydroponic system, and with synthetic nutrients and good SOPs around keeping your system clean, and you can definitely incorporate rainwater and condensate reuse into a system like that. Again, if it's in a controlled environment, and you have the ability to capture those reclaimed sources. So absolutely.
Yeah, and one thing that I had no idea of until I started consulting and meeting people like you, and I think the cannabis industry gets a lot of credit for this. These skids, they call them skids. It's like palletized water treatment. It's all on a palletized skid, all the equipment that you need, whatever it might be, and you can pick it up with a forklift, bring it in, and drop it in your water treatment room. If I got that description right.
Yeah, I think the advancement of I will say the advancement of the cannabis industry has advanced ag tech tremendously, because what we've historically had is very large systems, very large fertigation skids or water treatment skids that were really not economical for smaller grows. And the advent of growing in a much smaller space with a higher commodity, it advanced different technologies to allow it to be used on a small scale. And so yeah, those technologies are out there, and they can fit the budget of a smaller operation.
Thank you. I'm going to actually, I have no idea how to answer this. Andy, you're getting the hard question.
Okay.
Andy, one of our attendees today is asking, what must we do with heavy silica in water? Silica. I know that silica sometimes is put in on purpose to improve the strength of cell walls and improves things like rice from lodging, which is falling over. But this person is looking at, I guess they're worried about a toxic level.
I'm not familiar with the term heavy silica, but normally silicon is present, anywhere between 30 to 100 milligram per liter. Simple answer, if you want to get rid of it, is reverse osmosis.
Very good.
Yeah, I was going to add that there's ion exchange technologies
For sure.
that would not be applicable to hydroponic plant production because of what we talked about earlier, the exchange of those ions, like the chiller example. But RO is the traditional means of removing silica.
Great, thank you. Oh, now Kyle gets a hard one. Here's a question from Joe, one of our attendees. And before asking you this, I'm going to point out that in the best practices guide, we have a whole chapter on bringing it all together, where we have diagrams, schematics that we spent a lot of time on. Carmen Azzaretti from RII, our operations and engineering manager, spent time in getting information from the industry experts about putting it all together. The water coming in, how it's treated, how it goes through the greenhouse, it comes out, what it's done with it then, dirty tank, cleaned up, sent back through the system. I mean, there's schematics are there. So if we can't answer all of this now, I would refer you to that. So here's the question, Kyle. When you have decondensate, and I presume they mean condensate, when you have condensate, tray runoff, which must be leachate, and rainwater all going to the same reclaim tank, how do you advise treatment?
It's a great question.
Okay.
Yeah, it is actually a pretty simple answer in my experience. People doing that are doing it at a very large scale with very large facilities. So the rainwater pond reservoir is outside, and it's a very large body of water. You want to condition that water. You want to provide oxygenation, oxidation, some type of conditioning to keep that reservoir turned over, mix, minimize dead zones, keep it disinfected, keep it aerated. And then when you go to reuse it and pump it out of that reservoir, it would go through a filtration process and an additional like inline disinfection stage, whether it's UV or chlorine or whatnot. That treatment train I just described is there's nothing proprietary about that. It just, hey, condition the water so it doesn't lay stagnant, filter out constituents that might build up, make sure you hit it again and disinfect it prior to giving it to Andy and the hydroponic team.
Thank you. You know, I've got a question from a registrant that I'm going to ask both of you. We'll wrap it up with this question. I'll give you each a couple minutes. And I want to thank the audience for all these great questions. Andy, we'll go to you first. What are you most excited about with your team's work this upcoming year?
Well, like I say, we're involved in numerous trials. So what we're doing right now, for example, in vegetables, we've got a great program with Philips Led Horticulture Solutions, where we're looking at water and nutrient uptake with low heat input. Yeah, so remember, LED lights, there's less radiant heat. We've got double screens in the greenhouse. We've got low pipe temperatures, and really, you know, we're really focused there on applying irrigation so precisely, yeah, to match it with uptake by the crop. And what really, you know, got me excited, you know, we got for example, we realized zero drain until the first harvest, yeah, because we precisely monitored what we were irrigating based on what the plant was transpiring in that system. Likewise, we manipulated it's probably a bit too much detail, but we manipulated the nitrate and chloride concentrations to affect the balance in the plant, while focusing that we maintained uptake of potassium, magnesium, and calcium. So that's a really good program of work. We're doing on strawberries. I think we're paving the way in our new business development department there, and achieving great results using precision irrigation, not copy paste, but copy paste the principles of irrigation management that we've been using in high tech veg over to strawberries, and the work that we've been doing in cannabis. You know, likewise. Right now we're flipping from propagation straight into the flowering stage. We're monitoring irrigation, you know, precisely, realizing again no drain through the almost through the cultivation, yeah, which is great because then I don't have a recycling problem. Wow. So that is you know, great work that we're doing within our trials program across the trials team.
Great. And you can follow Andy on LinkedIn and get updates on this stuff. I know I am. And I'm really excited. Particularly the strawberry work is just fascinating. It's something the industry.
I'm a social media mogul, yeah.
Kyle, same question to you to wrap this up. What are you most excited about with your team's work this upcoming year? And there's a lot of changes coming because you're starting up this new division of Arco Murray. Go ahead.
Well, apart from following Andy on LinkedIn, so it's a very exciting year for Arco Murray and for Blue Water. We had a great year last year. We're dealing with some of the largest, most sophisticated farms here in the United States, and you know, on a personal level, the innovations, you know, and the operational vision that they have for these farms in terms of water reuse. Some things I haven't seen at a commercial level, and we're very excited to employ them. But very, very sound, very sustainable, you know, water management strategies that are essentially going to be backed by a lot of data to be able to quantify results, which is something we didn't get into in this talk, but you know, something that's oftentimes lacking from this industry. So lot of stuff going on. I'm excited to, continue to, share that stuff and work with RII to, improve the industry.
Great. We appreciate working with you as well. So I want to wrap it up and thank the audience for joining us today in this webinar. I want to thank the USDA for their support of RII's work. Our special thanks to Kyle Lisabeth and Andy Lee for being our expert panel today. For Brendan McMillan of RII, I'm Rob Eddy, and thank you for your attendance today.